name is Leerin, as previously introduced. I am talking on behalf of SPIE Isotopes, a newly established US company whose roots lie deep within the heart of South Africa. South Africa is our heartbeat, as our CEOs like to say. And before I continue, I just want to thank the NSTF for this opportunity to showcase the work that we're doing in ASPI. I've titled my talk today, Enlightening Medicine with Quantum-Enriched Isotopes. And that's purely because I want to show the power of quantum and how it can actually be used to create life-saving isotopes that is sure to revolutionize both medicine and the world as we know it. I just want to make sure, can everyone see my laser pointer? I'm assuming yes.
Yes.
Fantastic.
But Leerin, you won't present tonight. See your notes.
Oh, really? That's pathetic. Okay, hold on. No one's doing that.
I just thought had to see your notes, but you're welcome to change it.
Hold on, let's see. Stop sharing. I'm just sorry. Just give me a sec.
Sure, no problem.
I don't know what happened. Let's try again. Is that better? Let's see now. You don't see any notes, right?
Don't see the notes now. No.
Okay, great. Okay, I'm so sorry about that. Thanks, Prof. I didn't even need to look at the screen. I knew his voice from from a mile away. Okay, great. So sorry about that, everyone. Let's just get back on track. So, as I mentioned, I am from ASP Isotopes. And all the way right at the bottom is Enlightening Isotopes, which is a subsidiary of ASP South Africa. And I have the delight of actually leading this team as of 3 months ago. So this is the group, and I would like to introduce you to them. So it is a multidisciplinary group that's made up of everyone from physicists to project managers to lab assistants, and we are currently expanding the team. But our team is not complete without our wonderful research partners at both Wits University and Stellenbosch University. And yeah, well, this is what makes the dream come true, so to speak. So what is Enlightening Isotopes and how does it fit into this grand scheme of things? Well, at ASP Isotopes, what we are focused on, or well, in Enlightening Isotopes, we're focused on making the stable isotopes. But as you would have seen, we have a subsidiary called PET Labs. And what PET Labs does is they take those stable isotopes, they put it in their neutron reactor, and what you end up with is short half-life radioisotopes. And these isotopes then get sold or given to patients in need for various medical treatments such as oncology or PET scanning. As you can see, we have various isotopes planned for our own department in the upcoming future. But for today, what I actually want to focus on is our first enrichment facility, which is the ytterbium-176 plant. And in particular, what this isotope does is it goes into, or it decays into lutetium-177, and it's used for oncology treatment, which I'll explain further. So the bad word that is in the world today, cancer. Everyone that is around would have been somehow affected by this horrible disease. And actually, right now, there's over 18.5 million new cases that is currently going on, with over 10.4 million deaths globally. The most common cancers range from breast cancer all the way to stomach cancer. But the one that I want to focus on today is prostate cancer for all the men out there. So prostate cancer is the most common male cancer globally and locally in South Africa. And those numbers are only increasing by the day. So this is definitely something that needs to be addressed, and it is something that is definitely ongoing in the world right now as a crisis. The good thing is that we have wonderful scientists that are in the world right now and a lot of research going on. And a so-called wonder drug has emerged from overseas, and that is lutetium-177. So this revolutionary cancer treatment, I've just taken an extract from a paper, one of many successful papers actually. So I want to bring your attention to the baseline of this picture over here. On your left-hand side over here, where it's really dark, you can see this gentleman had prostate cancer. It's really dark in the scan. But after 2, 4, and 6 cycles, you can start to see that that tumor actually started to decrease in size. And what they actually found continuously over all of these different research papers is that over 75% of patients that were treated with this lutetium-177 were successful in their treatments of getting rid of cancer. And over 51% of patients actually had more than 50% reduced after just once a few rounds of this treatment. So this is definitely something that is revolutionizing the way that we do medicine, specifically for pancreatic oncology. And how does it actually work? So lutetium is a drug that actually attaches itself to the cancer cells and only the cancer cells. And once it is absorbed into the cancer cell, it actually emits the short-range radiation that damages the tumor from the inside and leaves all the other cells, the healthy cells, behind unaffected. So if we had to compare this treatment in comparison to a normal oncology treatment, such as external radiation or chemotherapy, it is not as invasive or harmful as those kinds of treatments. And you can treat multiple cancerous sites at once. It also doesn't rely on things like your immune system, and it can be used for much later stages of cancer. So it is definitely a precision drug without extensive damage, and it is something to consider going forward in the world. So how do we actually get this lutetium-177? Well, the traditional route is to actually start with lutetium-176. Then take that and load that into your neutron reactor, so somewhere at PET Labs as an example. And then this would radioactively decay into your lutetium-177, which is the desired therapeutic isotope. And this would come as a liquid form that's then injected into the patient. However, as you would have noticed, there is this little doohickey over here in this decay mechanism. And that is actually an undesired isomer that is a radioactive impurity. It has high energy, and as you can see, it has a very long half-life, so it stays in the patient's body for very long, and it makes the patient have unnecessary amounts of radioactive stuff in their body. So this is not something that's desired, and in fact, we actually don't want this at all. It also poses other challenges for medical practitioners. So in fact, what we actually want is a route that does not include this at all. And so how do we still get the therapeutic isotope without having this isomer or all these other impurities? Well, there is a new route that has been proposed, and that route includes something called ytterbium-176. And this is where ASP isotopes, or specifically enlightened isotopes, comes into play. The ytterbium-176, as you can see, would then be loaded into the neutron reactor. It would go to 177, which has a very short half-life. And then this allows the medical practitioner enough time to actually inject 177 directly into the patient's body. So in this route, as you can see, we don't have this undesired isomer. And this is actually the route that is more plausible for different treatments. Okay, so I don't know what's going on here. In a second. Okay, there we go. So what is ytterbium-176? Well, I'm pretty sure that if I had to give everyone a pop quiz, no one would know where to even look for it on the periodic table. And it's actually because it's all the way down there where the lanthanides are. Ytterbium is actually a rare earth metal. And well, the one that we want is actually an isotope. So this begs to the question, what is an isotope? So for all of those that are very technical, please excuse the simplicity, but it's just to make sure everyone's on the same page. So to understand what an isotope is, you first have to understand what an atom is. And just as a recap, an atom has a nucleus, and in the nucleus you have a neutron, which is no charge. You have a proton, which is positively charged, and then you have a bunch of electrons orbiting around this nucleus that is negatively charged. Okay. Now let's just go to the hydrogen atom, because this is usually the simplest one. In the hydrogen atom, well, one of the most common isotope that you would find is hydrogen-1, which has one electron because it is neutrally charged, but it has no neutrons. And in nature, 99% of all hydrogen that you would find is this hydrogen-1. However, at a 0.015%, you would actually find hydrogen 2. And what you would see is that that actually has 1 neutron. In both cases, these are not radioactive. And then you would find trace amounts of something called hydrogen 3, which actually has 2 neutrons in it. In other words, what are we saying here? That isotopes have nuclear masses and stabilities that are different, even though they are of the same element. Now, if we had to go to something a little bit more advanced, where there is multiple electron levels or multiple orbitals, what would we actually see? Well, you would actually see between different isotopes, the energy levels have slight differences in their energies. And to understand this a little bit better, let's go down to a sock analogy. So if I had to compare hydrogen, carbon, ytterbium, all these different elements in the periodic table, you would be able to notice those differences. They have microscopic differences, okay? But what isotopes are, is they are actually like the same color sock, but their differences are very, very tiny. In fact, their differences are on the quantum level. Okay, so this is the comparison between different elements versus different isotopes. So back to ytterbium. Ytterbium actually has 7 different isotopes, and these are all the isotopes. It's from 168 all the way to 176. Okay, and these ranges are the different abundances of all of these different isotopes. And the one that we actually want, as I mentioned, is ytterbium 176 all the way over here. So how do we think about this in just like a simplistic concept? Well, I like to use jelly beans. So I imagine that the ytterbium the ytterbium metal is actually just a big pack of jelly beans that have all these different colors in it. And what I actually did is you think of it as assigning each of these isotopes different colors of jelly beans that belong in this big packet of jelly beans. Okay. So in other words, all the jelly beans are similar, but they're not identical, because why? The colors are different. And in some cases, even though moms and dads might argue, the flavors are different. Okay. So what does that actually mean? Well, in our bag, what I'm trying to say is that there is about 0.12% of the white ones, but there's 32% of red ones in this packet. And that's the isotope abundances that you would find in nature. And if you added all of these up together, what you would end up with is back to your big bag of jelly beans. Okay, so what are we doing again? We are trying to get only 176 because we want to follow this new therapeutic radioactive decay process. Okay, so what do we have to do? We have to remove the one that we want from all the other isotopes. And the reason for that is because all the other isotopes, I said here, it tastes yucky. But that's purely because all the other isotopes, if you had to put it through this process, you wouldn't actually end up with lutetium-177. And then you're back to square one, which is I have isotopes, unwanted isotopes or unwanted isomers or impurities in my system that's not good for the patient at times. Okay, so what do we have to do? Well, we have to take our bag of jelly beans and actually sort them out into their different colors, into their different isotopes. And then we have to isolate that 176, so that jar of yellow jelly beans. Okay, and we need to understand something, that this is never 100% pure. It will never be 100% efficient, but we need to try and get to as close as possible to that 100%. So over 99% of the jar should contain your yellow jelly beans. Okay. So once we have our pure, ytterbium 176, our pure jar, then we would be able to deliver it, and then this process would actually work. Okay, so enough of jelly beans, back to reality. This is what I'm actually trying to say. The natural ytterbium, we would have to take it and undergo some process where we only have ytterbium 176 left in our jar that is 99% pure. But the problem is, how do we actually do this in reality? How do we do this separation, which the fancy word for that is enrichment, okay? So there are a lot of various techniques that actually exist. And these go from gaseous diffusion to centrifuge to molecular laser isotope separation and even chemical separation. So there's a lot of things on the market. But the problem is that they are not suitable to actually enrich or to separate ytterbium 176. And the reason for that is because with gaseous diffusion and centrifuge, as an example, there is no stable gas compound that is suitable for ytterbium. If we had to actually successfully do that, it is chemically unstable. And it would also require multiple stages. In other words, you would have to build multiple centrifuges and then have this cascading effect. So that is not suitable. If you had to do the molecular laser isotope separation process, it requires you to actually have a stable molecular version of ytterbium, and that's also not suitable. That also doesn't really exist. And it is also not a selective process. With chemical separation, you're working with a lanthanide. And lanthanides have very small differences, chemically speaking, between different isotopes. It's also not selective enough. So we have a problem. And this is where we need to really think and scratch our heads and say, how do we actually solve this problem? Well, the answer to that is we have to resort to quantum techniques. And what does that mean? Well, quantum just means working with really, really small, the smallest discrete unit of energy or matter. And these can be things like photons, electrons, quantum of energy. In other words, the idea that your atom has discrete energy levels and your electrons can occupy only those discrete energy levels. They can't be somewhere in between. Okay. So isotopes like ytterbium have differences on the quantum level. And as I mentioned now, that's because they have different neutrons, okay? So the nuclear stability is different. They decay in different ways. But it also means that the energy levels are slightly different. And that's because of things like hyperfine splitting, it's because of mass shift, it's because of field shift. And these things give rise to your energy levels being slightly different. Remember the analogy that I mentioned earlier. So what this actually means is that your isotopes have unique quantum fingerprints, okay? And we are going to use this idea. So using your quantum fingerprints, you can actually identify and separate your isotopes. In other words, you can pick apart your different socks just based on the patterns that they have. To give you an idea of how small the differences are, let's use this slide over here. So if I had to take my socks and actually put them in a microscope, that would be 10 to the minus 6 level. So that would be micro level. But what we are actually saying is these differences, these quantum fingerprints occur on a picometer level, which is 1,000 times smaller than a microscale level. So it is really, really tiny. And so now we beg the question, how do we actually exploit this picometer differences in energy levels when it is so tiny? Well, the wonderful thing about living in the century that we do is that there is something called lasers. And lasers are actually accurate enough down to the picometer level that you can use lasers to be the solution to actually deciding how you're going to adjust and actually sort and identify these different isotopes. So this brings us to the idea of quantum enrichment. And I like to say to investors and to people what quantum enrichment actually is. My elevator pitch is that it is rare earth metal refining with lasers. So that sounds like a mouthful, but what is that actually? So I'm going to break it down for you. What you're going to think of is isotopes have their favorite flavor of milkshake. So each isotope is like a little kid, and each kid has its favorite flavor of milkshake. Now, milkshakes are similar, okay? They have similar ingredients, but it's the small differences in the ingredients or slightly different ingredients that makes it unique. The milkshakes have to be prepared in a very specific way. And what you need to remember is that isotopes are allergic or they dislike the ingredients of other milkshakes. So it's very important that you stick to the exact ingredients that your isotope wants. And if your isotope likes the milkshake that you've given it and it is exactly the one that it wants, it will drink a lot of the milkshake up and it will have a sugar rush. And that is how we're going to be able to identify and sort out the isotopes like our jelly bean jar. That is how we're actually going to be able to do that. So let's explain how that actually works. So back to our energy levels. Okay, so if we wanted a strawberry milkshake, our isotope 176 wants a strawberry milkshake. what do we have to do? We have to use the correct ingredients to get the strawberry milkshake, and we have to follow the recipe exactly as is. If we miss a step or we do something different, instead of getting a strawberry milkshake, you might end up with something like a chocolate milkshake, which is not going to work. Okay, so how do we actually do this? Well, what I'm actually saying is that we would have 3 different lasers, and these different lasers will be tuned to make the specific ingredient that's necessary to make the milkshake that you want. So the first laser will be tuned, it will be precisely shifted in terms of color and in terms of energy to produce the first ingredient. The second laser, the second ingredient, and the third laser, the third ingredient. Now you have all of these different ingredients, and then you have to put it together and blend them up to make your milkshake as you want. Okay, and once you have your milkshake, you have to deliver it to the isotope. So what are we actually doing when we are delivering this milkshake to our isotope? Well, if you think of the isotope, right on the end of the isotope's atomic structure is something called a valence electron. And by giving it all of these different ingredients, what you're actually doing is giving that electron enough energy to move up this ladder and eventually pop out of the atom. So this is what you're doing over here. You are ionizing. That's what it means. And now the isotope, and only the isotope that you want, will become positively charged. So in other words, successfully making and delivering a strawberry milkshake, in this case, to 176, will ionize ytterbium-176 and leave all the other isotopes unionized. Okay. So if I had to put this all together, what are we actually doing? Well, here's it over here. I take my ytterbium metal, so I take my jelly bean packet, I heat it up. What am I actually doing? That is back to the analogy of I'm sorting it out into the different jars. So I'm loosening it up. Then back to our milkshake analogy, I take the milkshake that I've prepared with all of my lasers, and while the ytterbium is floating around, or all these isotopes are floating around, I let the laser interact with this stream of gas of ytterbium. And what would happen? Well, only the 176 would drink its strawberry milkshake, and all the other isotopes will be left behind. And then what have I done? I've done exactly what I just said, which is you're going to ionize ytterbium-176 only. And what you need to do is have a negatively charged plate, because opposites attract. And in that way, I'm able to completely extract the ytterbium-176 that I have separated. And that is the idea of the jelly bean jar now being isolated. So what does it look like in the lab? Well, in the lab, it's basically 3 critical systems. You have your laser system, as I mentioned, and those are 3, you make up your 3 different ingredients. Your optical system would then be blending or mixing all of your different ingredients together to prepare your milkshake and then deliver your milkshake to a target vessel, which is where your ytterbium-176 actually drinks it up. And what does it look like in the lab? Well, this is actually what it looks like in the lab. You would have your lasers, your optical system, and then your vessel where the magic happens. So to bring it all back into one idea, what are we actually doing again? As I said, you are making your ytterbium-176, you are separating it from all of your different isotopes. You then take it, and our wonderful chemists know exactly how to do this with very high yields. And you get ytterbium oxide, which is very easy to transport. It's also very easy to load into the reactors. Your ytterbium oxide is then sold by ASP, as an example, to a company like PET Labs. And PET Labs would then take your ytterbium-176, bombard it with neutrons in the reactor when the doctor and the patient needs it, and then they would have lutetium-177. And this lutetium-177 will then be given to the patient that's in need, and hopefully by doing that, we have saved a life. So in summary, what are we actually doing at ASP? Well, let's just start from the beginning. Pancreatic cancer is a global crisis. And there are new drugs that are offering extraordinary breakthroughs to deal with this problem. The problem is that we need very highly pure isotopic samples, like ytterbium-176, and it needs to be in gram to kilogram quantities. Traditional separation methods aren't suitable, and this creates a very high demand and a very low supply. So come for business, that is absolutely the market you want to be in, but it also helps us, or it gives us a platform to actually meet the needs of people for a very long time to come. Traditional separation methods aren't good, and yeah, as I said, that's why we have a high demand and a low supply. And we can exploit the quantum differences of isotopes to actually separate them. And this is possible by using lasers and this idea of quantum enrichment. And in conclusion, quantum enrichment enables the making of life-saving isotopes, and we hope to make many more isotopes that are life-saving within the next few years beyond ytterbium-176. Thank you very much, and I hope this was a very insightful presentation.
Thank you very much, Leerin. I will never look at my... And I'm sure for some reason I'm feeling very hungry at this stage.
You can see I was hungry when I made the presentation.
Yes. It's wonderful. I really think that you've brought across some very technical stuff in a very user-friendly way. It gives one hope. Gives me hope that cancer can be treated in a precision manner, and that you're assisting in doing that.
Sure.
Do you know about, of course you do know, about NuMeRI, the Nuclear Medicine Initiative?
No, I'm sorry. I actually am very behind with a lot of those kind of things. So no, I haven't heard of it.
I'm not surprised. You are busy doing what you have to do.
Yes, I do leave that to our wonderful management team. They are very on top of that.
Well, it is. I can tell you, it's a new facility that was launched about 2 or 3 years ago at Steve Biko Hospital, and it is for diagnosis and therapy to happen at the same place. So it's very equipped to do various kinds of cancer treatments. But there certainly is a lot of interest in cancer treatment, and the more precisely you can do it, the better, because the traditional methods of treating cancer are so deadly, I would say.
Yes.
They are so destructive. Let's see, there are other questions here. Right. Ronald says, a great talk, Leerin, thanks. What are the energy requirements of quantum enrichment?
So I have to be very careful on what I say. I'm not allowed to give too much technical information. From a production point of view, I would say this is our standard saying in ASP, you can do it in your garage, which is actually an insane concept to imagine that you could do something so great on such a small scale. But that's the beauty of actually working with lasers and working with such small equipment, is that you don't need these big facilities to actually enrich to the level that we want. If you had to do it with gas centrifuge or all these other processes, we have those in our company, and it actually takes up a whole factory space. But the lasers fit in the equivalent of 3 or 4 office spaces combined, and I know that because that's exactly what we did. So the energy requirements from that point of view, very, very low. I hope that answers the question.
Gosh. Yes, I think it does. Anyone want to ask a question in person? Please put up your hand. I certainly found this very interesting. So lutetium, how common is lutetium? Is it easy to to acquire, or is it very expensive?
So I have yet to be corrected. I mean, I'm not on the commercialization side, but as far as I know, lutetium it's only starting to get traction now. The prices for these lutetium treatments are quite expensive. It's
Yeah.
not something that I think is just laying around. But I think as the supply of ytterbium becomes more, hopefully by ASP, then that prices would go down. And that's the idea, is that for us, from a business point of view, because lutetium is getting sold at such a high value, it makes sense for us to jump into that market as well.
Right, right.